So section 10.1 is called area under the curve. And if you recall what we took a look at in the review and preview, is really, let's take a look at this basic example. We were looking for the area underneath a line here, right? And that's a simple trapezoid. So we can just use basic algebra formulas to find an area here. The problem is, okay, is when this is not a straight line, this no longer is a trapezoid. So the trapezoid formula doesn't work. But the cool thing is that we can use calculus to find the area under a curve, even though this curve is not straight. And that's sort of the basis behind, what we're doing here in chapter 10, area under the curve. Okay? And so if you look on page 449 in your text, and here it is right here, here's an example where, hey, we have a curve that does not have a straight edge here. Okay, this is some function that is not linear, and what we're looking for is the area under the curve in this region, and it's bounded from A to B. Okay, so it's similar to what we just took a look at with the trapezoid. So we do have an upper boundary and a lower boundary here, but what the problem is that this varies greatly, this top part. Okay, so we're looking for the area to the right of this A value and to the left of B, and bounded by the x-axis and bounded by the function. Okay, so when we talk about the area problem, we're talking about how to find an accurate area for this region. Okay, obviously it's a weird shape. So if we take a look at this example here, this is very similar to the one we just looked at. So we're going to go with something pretty basic, and we're going to try and draw some connections here between calculus and this area. So in this example, again, you don't have to write this down. It's in your textbook. Just kind of watch along as we go. But the example is, what is this area underneath here? And we know that this line right here is given by the function y equals 2x plus 1. And we're looking for the area between x equals 1 and x. Okay? So now by doing this, we are going to calculate what an area for the function is in terms of x, not an actual definite area, a number, but we're going to try and get basically a formula, right, for this area. So we're looking for kind of like a formula. So if we use the trapezoid area formula, okay, this is what we have. The area is 1/2 the height of the trapezoid, which would be right here between 1 and x. So that is x minus 1, times the length of A and the length of B. So A would be the value of this function when x equals 1 is placed in there. So 2 times 1 plus 1 would be 3. And then, of course, the value of this length right here is the height, right? Or is the value of the function itself evaluated at x, which is just 2x plus 1. So this is different from the review and preview. Again, just one more time, we don't have a value for x here. We just have x in there. And it's going to give us a bit of a formula. So when we simplify all this out, we get the area function is x squared plus x plus 2. Which means that if we had x equals 2, we could simply plug 2 in for x and immediately find the area. If this x was 10, we could plug 10 into the x there and into the x there and find out what the area is, right? Okay? So this is making sense, right? Just like the slope of a tangent line. When we took the derivative, we had, the derivative is, whatever, 2x plus 5. And at whatever x value you want to find the derivative for, you just plug in that x value in, right? And so, similar thing here. But what I want you to notice, and this is the really neat part, is that the area function here in this example is x squared plus x plus 2. Okay? The derivative of the area function is 2x plus 1. Now that 2x plus 1 is the same as the function that created this boundary here. Okay? Now you might think, well, this is a trapezoid, Mr. Maxwell, so maybe that's just going to happen. But it is interesting to note that it's the derivative of what the area is in fact the function up here. And that's going to be super important for going forward, okay? Because this connection is really neat. So what we see is in example 1, the derivative of the area function turned out to be the function that defined the straight line or the upper bound. Now notice in these questions where we have an area problem, we don't have a straight line, but yet the upper bound is still f of x, right? So back here, right, the derivative of the area function, okay, was this, and the area function itself, that derivative, sorry, was f of x. Okay, so you come back to this one here, and the area problem can be solved now if we can establish that the relationship of the derivative of the area function is f of x. That's the line up on top. Or another way to put it is the antiderivative of the function, the upper bound there, the antiderivative is the area function. Okay, so let's say that f of x was the derivative itself. If we want to go back, we would get a of x, right, if we took the antiderivative of that. And that's the key point. That's the key point. So we're dealing with antiderivatives here. We're connecting antiderivatives to the area under a curve. So I'm not going to spend a lot of time on this right now. This is sort of the proof of this. And you can see they use limits. This looks like an awful lot like a derivative there, right? And so anyways, once it's all boiled down there, they can prove that the derivative of the area function is the function itself there. Okay, so this is the proof, which we're not going to go into, but you can take a look and read that if you want. Okay, so what we've established so far, okay, is that the area function, okay, when we take the derivative of the area function of this this sort of situation right here, we're looking for the area of this region here. If this is f of x, the area has something to do with the antiderivative of f of x. Okay, so again, remember this capital A is capitalized, therefore it sort of represents an antiderivative, right? It's not capital F because they want to connect this with the area. So you want to write this down in your notes here as a summary of what we just talked about. Taking the antiderivative taking the antiderivative of the function, and that is the line or the curve that forms the upper bound of this region, in this sort of situation like this, is equal to the area function of the region. And we will continue this lesson next day.